About 17% of the total population in the United States have hearing problems. According to World Health Organization, 360 million people worldwide have disabling hearing loss. People with hearing disabilities are incapable of responding to sound sources in the environment and thus are more prone to accidents. They cannot respond when their name is called or move away when a vehicle approaches from their backside. Our vision is to create a wearable sound localization and visualization device that will enable the deaf to respond to such stimuli by augmenting the visual information available to them. The sound in the environment is captured using 2 or more microphones arranged in an array. The signal processing for the time being is done in a computer using NI lab view. The output is relayed to the user with the help of a transparent display module placed in the front of his or her eyes. This is a representative visualization of what we hope to achieve. The direction of arrival of sound can be inferred by analyzing the signal incident on a microphone array. This direction is then represented as colored blips in the transparent display. An important part of the project is mapping the frequency to RGB values representing a color. For this, the frequency of the signal has to be known. Each signal is made up of many component signals. For practical purposes, the frequency of a signal is considered as the frequency of the component signal with the largest amplitude. For the time being, the signal is received using the built-in microphone in the laptop and is analyzed using NI LabVIEW 2012. The top graph shows the input signal. The bottom graph shows the power spectra of the input signal after doing a Fourier transform on it. The component frequencies are clearly visible in the lower graph. The frequency of the signal is seen in the maximum frequency component indicator. This frequency is then mapped into a color value, which is then passed on to the transparent display. In our mapping, lower frequencies are reddish and higher frequencies are somewhat bluish. Now, we introduce a dual-tone multi-frequency signal to the mic using a mobile phone. As can be clearly seen, the frequencies are resolved in the lower graph and the maximum frequency present is displayed in the indicator.
Now 1, 2, 3, 8.
This is a transparent display module. The red blip represents the direction from which the sound arrives, and the blue blip is for reference and acts as the center. The vertical band, which is currently blue, indicates that the signal arriving is of a higher frequency. Determining the direction of arrival of sound involves calculating the time delay of sound on arriving at the different microphones. This LabVIEW program simulates such an environment by allowing the user to manually supply certain samples of delay to the signals. The graph contains all 4 signals arriving at each microphone. Each signal is shifted to the right with respect to the previous one because of the delay that was manually supplied. We can see that the time delays obtained after processing is in correspondence with the manual delays supplied. This is a demonstration of how direction of sound from a source moving around the user will be represented in the display menu.